Hello everyone, this lesson is about equilibrium of rigid bodies, that is rods, such as a ladder modelled as a rod leaning against a wall, and problems involving what angle it might rest at before it slips. So it concerns section 7.4 on page 142 of the Statistics and Mechanics Year 2 book. So we've considered the equilibrium of a particle, where we have to have the total forces must add up to zero. So you have here the three forces: the weight, friction, and reaction, all have to add up to zero. Friction, weight, reaction. We do that by the sum of the vectors must be zero. And we've also considered the situation where you have a horizontal rod, where we have reactions here and here. Let's say that's R1 and R2, and let's say it's a non-uniform rod, maybe the weight is there. And in this case, the sum of the forces must be zero, and also the sum of the moments of the forces about any point must be zero. So for a particle, the total force must be zero, and for a rigid body, we have two things: the total force is zero, and also the total moment about any point, total moment of all the forces about any point must also be zero. So these problems, the particle and the horizontal rod, are two problems that we've covered already. What we're going to do now is problems where the rod is not horizontal. So I'm now going to go through example 7 on page 142. We have it here: a uniform rod AB of mass 40 kilograms and length 10 meters rests with the NA on rough horizontal ground. The rod rests against a smooth peg C, where AC equals 8 meters, and the rod is in limiting equilibrium at an angle of 50 degrees to the horizontal. Find the magnitude of the reaction at C and the coefficient of friction between the rod and the ground. So the first thing to say is, what is a peg? Sometimes people are not sure what we mean by that word in this context in mechanics. Well, a peg, here's a Google peg, and it comes up with things like this. There, it's basically a something that you hang your coat on. So here's a row of pegs. That's a peg. You would screw it into the wall, a bit like that. And it's here you can see this is what you would do with a row of pegs. You would hang things on them, or you could lean things on them. So in the context of the mechanics problems, what it is just a point. We would model it as a point where a rod can lean against. So we have, in this case, a rod resting on two things: a ground and a peg. So the horizontal ground and the peg. So the first thing we have to do is draw this situation. Okay, so here you have the ground, that's horizontal, and here you have the peg. And the peg, as you can see, really is modelled as the point. The blue line is the rod, and there's one end on the horizontal ground. That's A. We'll mark that in. That's A. And B is the other end, and the peg is at point C, which is there. Okay, so the next thing to do is to put in the forces. So what forces do we have? Well, it's a rough ground, so at A we must have friction and reaction. Well, reaction is normal reaction, and that is vertical at A. We'll call that R. And also we have friction, and friction is in this direction because it is a force that's preventing the end of the rod slipping towards towards the left, as it would do if the ground was smooth. Then of course you have the weight. Well, we have a uniform rod, so the weight acts at the centre. And then we've got the forces at the peg. Well, the effect of the peg is to stop the rod AB from falling onto the ground, and that is done by a force at C. Now, because it's a smooth peg, and see here, smooth, there is no friction, so we there is just one force, the normal reaction at C. We'll call that N, and that was F. Okay, now the next thing to do is to put in the lengths. I didn't put in the I've also got to put in the weight. The weight is 40 kilograms, so that is 40 G newtons. Okay, so what lengths do we have? It's 10 meters, and AC is 8 meters, and of course it's uniform, so the weight acts at 5 meters. So from A to the centre would be 5, and then we've got 8 meters to C, so that would be 3 from the centre to C, and that will leave us just 2 from C to B. And we've also got the angle, 15 degrees, that A rests on the ground. Now it also says that the rod is in limiting equilibrium. If you remember, what that means is it is just about to slip at A, and when it's just about to slip, friction is at the maximum value, and F equals mu R. And the two things we have to find are the magnitude of the reaction at C, so we need to find N, and the coefficient of friction between the rod of the ground, mu. So part A is to find the normal reaction N, normal reaction at C. Now the way to do this, we apply the two conditions, the fact that the sum of the forces must be 0, and that means the forces must be 0 in any two directions, and the sum of the moments about any point must be 0. Now to find N, we don't know R and F, and we would see that R and F both pass through A. So if we took moments about A, we would get an equation which doesn't have R or F in it, and we know the weight, and we therefore should be able to find N. So that's what we should do. We will take moments about A. So we write this moments about A. I like to write it more like A, and that means taking moments. So what is the because it's the turning effect about A. And if you remember what that is, how you calculate the moment, it's force times perpendicular distance from line of action of the force. Well, N's line of action is perpendicular to the rod. So the perpendicular distance from A to the line of N, and that's a line that where the force acts along, the line of the arrow, which is infinite, is just N times the distance 5 plus 3, 8. And then we've got the 40G. Now the 40G turns the other way. N, as you can see, is turning anti-clockwise, and I'm indicated that anti-clockwise would be positive. So N times 8. The 40G turns clockwise, so that would be a negative moment. And it's minus 40G times, now we've got the perpendicular distance from the line of action of the force. So here's the line of action of the force, like that, the line that goes along the arrow, and so that's a perpendicular from A, so A to that point is this distance here. And in that distance there, in the triangle we have here, we have the angle theta at A, 15 degrees at A, and we know that cosine of 15 degrees is the distance we require divided by 5, the hypotenuse. And so that distance we require is 5 times the cosine of 15 degrees. And because it's in equilibrium, that equals 0. So if I divide that equation by 8 and put the 40G 15 cos 5 cos 15 on the other side, when I divide by 8 gives you 5G, which is 9.8 times cos 15. No, times 5 times cos 15. And that comes to 236.65 newtons. So we'll make that 237 newtons to the 3 significant figures. So now we need to find mu. Well, mu we get from the fact that it's in limiting equilibrium and F equals mu r. Well, in order to do that, we have to use the other condition for equilibrium, which is the sum of the forces is 0. So we have because I can only record 15 minutes on one video, what we need to do is go to the next video now. Yeah, sorry about this, but I went over the 15 minutes, so you must stop this one and go to the next video just to finish off that question. Okay, thank you very much. See you in a minute. Oops.